Okay, now we're doing lesson 2 of beginning algebra, or algebra 1, however you want to say it. Lesson 2, we'll go over real numbers, what it means, and different things that you must understand in order to progress into algebra. First, we're going to draw on what's called a number line. And on this number line, we have both positive and negative numbers, also including 0. So if we have a positive 1, we also have a negative 1. We have a positive 2, we also have a negative 3, and so on and so forth. The natural numbers lie between 1 and greater than 1, whatever it goes up to, we'll just say positive infinity. Whole numbers include all of the natural numbers plus 0. So from 0 to positive infinity. The term integer indicates all the natural numbers and whole numbers and all of the negative numbers that are included. So we have 1, 2, 3, 4, 5, and all up to infinity plus 0, plus negative 1, 2, negative 2, negative 3, negative 4, all the way down to negative infinity. This would include all the set of real numbers that we will be working with. There's also numbers in between each of the whole numbers, or integers, like negative 2 and negative 1, because we can have negative 1.5 and negative 1.2 and 1.7 and 1.8. They get closer and closer to 2, but they don't actually reach 2. You can also go the other way and go 1.1 and so on and so forth. They won't actually get to 1, but you can go into infinity decimal places or fractions of that number. You can go in either direction and you can have an infinite amount of numbers there. You can do the same thing on the other side of the equation with positive numbers. Between 1 and 2, we can have 1.3, 1.5, 1.7, and you can have an infinite amount of numbers in between each of those two numbers. These in-between numbers are called rational numbers. Just like how integers have an infinite amount of numbers, there's also an infinite amount of numbers of rational numbers. Let's go into example 1. Say we have a sea level here, and we have a hill or a mountain, and we go up the hill, and we also can go below the sea level and go negative. Usually, when you have elevation, you indicate how much is above sea level, but you can also have what's below sea level indicated by a negative number. So say that we are above sea level 3,000 feet. Well, that would be a positive number because we're above sea. The sea level representing 0 would be 0. Anything above sea would be positive. Anything below sea would be negative. Say we have negative 3,000 feet below sea level. It would indicate a negative number. You have many values in between the 3,000 positive and 3,000 negative. And there's an infinite in between because you can have rational numbers. And that would indicate a fraction of that number. Example number 2. We have a bank account and we're graphing it over a day or days. We have an amount in dollars. We can start off positive because we like money in our account. We like having money to spend. We usually try to get more money, so it's a positive thing. But sometimes we can withdraw more than actually we have, and that becomes negative. So what happens over time? We keep spending and spending, or we keep saving and saving. So first we save and save and save and save, and then we start spending like crazy because we got a lot of money. Now we go below the 0 amount and become the dollar signs start becoming negative, indicating that we owe money to the bank. This will be negative money that we do not have and that we owe. At the top is money that we have, and it'll be positive because it makes us happy that we can spend it and get things for it. Similar, you can write this on a number line, which we drew earlier, as positive 100, or we can have a negative 100, and everything else in between. Which is better, or which is greater? The 100, which is positive, or the negative 100? Well, usually when you have a greater amount of something that you owe, which is $100 in your account, it wouldn't make any sense if you had negative 100 and that would be a bigger value because you don't own it, the bank does. So it's not a larger value to you, it's a smaller value. So the 100 positive is a bigger value than the 100 negative. Okay, let's go back to rational numbers. We can have 2/3, 4/5, however much we need to work with. So we have an infinite amount of those rational numbers. We also have negative rational numbers, like negative 2/3 and negative 4/5, and it continues to a negative amount. Where on the number line would we indicate 1 and 1/2? Well, it would be in between 1 and 2. Here we draw the 1 and 1/2. Now, where would be negative 1/2? Negative 1/2 would be between negative 1 and 0. Which one would be bigger? Well, it would be the positive value. So that would be 1 and 1/2 would be bigger. Usually, this is indicating anything positive of 0 or anything greater than 0 will indicate a larger value most of the time, depending on the context of the equation. So let's do number -1 and -2. Let's graph -1 first, right here, and -2 right here. Now, between these, which one would be bigger? Well, it'd be -1 because it's closer to 0, or which is closer to the more positive values. Even though -2 seems like 2 is bigger than 1, but it's more negative. But we want to get closer to the positive side, so -1 would be bigger. So let's count up what numbers we have and what type they have. Let's make a list of all numbers that we have. Let's make a list first of rational numbers. We have 1 and 1/2, -1, -1/2. Do we have any whole numbers? No, we don't have any more. We don't have any whole numbers. Do we have any natural numbers? No, we don't have any natural numbers. Do we have any integers? Yes, we have -1 and -2. Now, let's briefly talk about how to change things into usable forms sometimes. Fractions are not necessarily easy to work with, so we can change them by dividing them. So, say we have 3/5. What would you do in order to change this into a decimal? Well, we have the 3 on the inside and the 5 on the outside. What times 5 would equal 30? Because we need to change this into a larger number than 5. So we put 3.0. So we know 5 times 5 is 25. That's not quite right. 5 times 6 is 30. So we put 0.6 because we need to go bigger than 3. So we have to add on to a 0. And in order to add on to a 0, we have to put 3.0. So now we subtract 30 from 30, we get 0. So 3 divided by 5 would be equal to 0.6, which would be equal to 3/5 equals 0.6. Well, say we need to graph this. So let's make our number line. Between -1 and 1, we'll include 0. So between 0 and 1, we have 3/5, or 0.6. We know 0.6 is close to 1, so let's make the dot close to 1. Because we cannot graph 3/5 on the number line without really knowing what 3 divided by 5 is equal to. We have to change it by doing our division that we did previously. So now we have 0.6. We know 0.6 is closest to 1, so we can graph this correctly. Now let's do the same thing with 5/3. We'll put 5 in the box and 3 on the outside. Since we're going to need more than what this would be equal to, so we need maybe 1 or 2 decimal places of the answer. So we're going to put 5.0 so we can continue with the division in order to get 2 decimal places. So 3 times itself, so 3 times 1 will give you 3. What's left over is 2. So you bring down the 0, now you have 20. So on top you put the 1 and you put the point. Now we work with the first decimal place. 20 times, so we're left with 20. 3 times what equals 20? Well, we got 3 times 6, that would equal 18. That's close. So we have 20 minus 18. You're left with 2. We have a second remainder that is equal to the first remainder. It seems like this is repeating over again. So when we have a repeating decimal like this, then we simply just write it as a fraction, or we write it as a line over the number. So we can say 1.6 ... or 1.6 with a line over it. Or we can just say the remainder is 2 to make this into a fraction. Remainder is 2, and whatever you're dividing by, which is 3, you put it underneath. So 2/3 is the remaining value of 1. So we would have 1 and 2/3. Well, let's see what the decimal value of 2/3 is. We have 2 goes into the box and 3 on the outside. However, we want to find the decimal places after, so we need to add zeros to the end of this. So we need 2.00, however many decimal places you want to go. And don't forget to put the decimal on the top. So 3 times 6 we know is 18. But you're going to continue to get 6 because you're going to get left with the 2, and you'll have a 20 left over. And you'll keep doing 6, 6, 6, 6, because 3 times 6 is 18, and you'll keep getting 2's. So 2 divided by 3, you'll get 0.666666666. Keep going over and over. You can try it for yourself if you don't believe me. So we know that 2/3 is representative of the 0.6666. And we know that we have 1.6666. So we can represent 5/3 as 1 and 2/3, or as 1.6. We can write a line over it, indicating that it continues to repeat. The repeating value means it's an irrational number, that it will continue on for infinite. amount of numbers. So our 5/3 we can write as 1 2/3 or 1.6 with a line over. Let's go ahead and graph where we would put the 1.6. Draw our number line. Put the value closest to the 2 because it's almost 2, but not quite. So we would put it between 1 and 2, but closer to 2. If the value is negative, we would have a -2 and a -1. So 1.66 negative value, we would put it closer to -1, or it would be closer to -2. Okay, we'll do a quick overview of irrational numbers since we were already talking about them previously. So irrational numbers are things that repeat itself, like our famous number pi. Everyone knows pi, 3.14, but it continues, and we call these numbers irrational. We also have a square root of 2, which also repeats. If you do the square root of 2, you get 1.4142, and it keeps on going. So these values won't stop. They'll keep going, and you'll have numbers that will continue to not be added on, but it'll just continue with the number sequence. Okay, let's go over a brief recap of what we all learned. We learned about natural numbers, we learned about whole numbers, integers, and rationals, and now irrationals. Natural is from 1 to positive infinity. Whole numbers would include 0 and go through 1 and all the way up to positive infinity. Integers include all the whole numbers and natural numbers and anything that is negative according to them. Rationals are in between, like fractions. That would also include negative rationals. Irrationals are just repeated values or values that don't stop. These all make up the realm of real numbers. However, there are other numbers that are not real. They're also called imaginary numbers, but we won't have to go into that right now. That will be later on, further down the road of algebra. How about we do a couple more examples? Say we have 9/4. Well, let's draw our number line between -5 and 5. Now we do the division of 9/4. 9 divided by 4. How many 4s would make up a 9? Well, we're going to need more decimal places, so we need to put our decimal here. We know that 2 plus 4 is 8. We're left over with 1, so bring down our 0. But now we have 10. Put up the point, the decimal after 2. Let's not forget that. Now we got to figure out how many times does 4 make 10. Well, we can do another 2. That'll give you another 8. And you're left over with 2 again. This looks like it's going to keep going. So now we bring down the 0. 4 times what equals 20? Well, that'll give you 5. So our 9 over 4, or 9/4, would equal 2.25. Now we can draw on the number line where it will lie. It will be between the 0 and the 5, and between the 2.5. So it'll lie between 2.25. So I'm halfway in between the 2.5 and the 0. Okay, let's graph the -3.7. So let's draw out a number line, and the -3.7 would go beyond the -3 right here. Let's do another one. Let's say we have a -5/2, or 5/2. Let's do the division. How many times does 2 need to be multiplied in order to make a 5? Well, we can do 2 times 2, which is 4. That's pretty close. 4, and we'll go down here. 5 minus 4 will give you 1. Now we need to make a decimal place, right? So we have 5.0, and make sure you make the dot up above. So we have 2 point something. Now 2 times what equals 10? Well, that's 5. So we have 2.5. 2.5 would be the answer of what would be -5/2. So don't forget to put the negatives in your answer, because we're doing the -5/2. Now, another way to write -2.5 would be just to put the 2, and since a decimal is just a fraction, we can write this as a fraction. So whatever our remainder was, which was 5 minus 4, which was 1, before we put the dots, the remainder of 1 over 2 would give us 1/2. 1/2 represents 0.5. So we can say -1/2 plus 2, or we can say -2 1/2. Remember that you're actually adding the -2 plus the 1/2 to the 1/2. So let's make our number line, and we're going to draw the numbers, the dot, wherever we need to, where it would represent. Okay, so it's not between the positive values 2 and 3, and between -3 and -2, since it's a negative value. And since it's 2 and 1/2, it would be between halfway between -3 and halfway in between -2. Now we're going to see, if you remember, the number line without drawing it out. Which one is bigger? Say we have 5 and 0, and we say 5 is greater than 0. If we have this symbol going this direction, now if we write -3 and we make the line go the other way, this symbol represents less than. So we have -3 is less than 3. Now if we have -4 and we make the symbol go to the right, pointing to the right, then we have greater than again. So we have -4 greater than -10. Same thing, if we point it to the left, we have less than. So if we have 3 less than 20. So say we have 3 less than 20, that would just mean 20 is greater than 3. So we can rewrite this as 20 is greater than 3. We just changed the symbol around. And those two are equivalent because they're saying the same thing. Because 3 is less than 20, but 20 is greater than 3. They're saying the same thing. It makes the statement true. Let's talk quickly about absolute value. Absolute value just indicates any value within between the two lines will become positive no matter what value they are in between. So if we have x, a positive x between these two symbols, which is representing absolute value, would equal a positive x. Now if we have a negative x between the two lines, we would also get a positive x. All the things that happen to absolute value is makes everything positive. So it makes everything greater than 0. So say we have 3, absolute value of 3 would be 3. The absolute value of -2 would be 2. The absolute value of -8 would be 8. The absolute value of 7 would be 7. Now no matter how big the numbers get, like absolute value of -20 or 200 will give you 200, a positive value. It doesn't matter if it's positive or negative, you'll get a positive out. As long as the absolute values are between the value. So anything between those two symbols becomes positive. Now don't be tricked, because sometimes they will put a negative value on the outside of the absolute value symbol. That doesn't mean the negative on the outside makes it positive, but anything inside will make it positive. So if you have something positive on the inside and something on the outside, it changes the value. Okay, that concludes our lesson for lesson 2, real numbers, from our algebra lessons or beginning algebra. Thank you for watching. Please subscribe and like our videos. If you have any questions, please comment down below.